When to apply these principles? These principles add complexity, more interfaces, more indirection, more classes to understand. So you need to apply them strategically where benefits outweigh the costs. You apply them for integration systems connecting many external services. Now, when integrating multiple third party APIs, databases, or services, these principles are essential because the external landscape changes constantly. APIs update, services deprecate, new providers emerge. Designing for these variations makes inevitable changes manageable rather than catastrophic. Use them for processing pipelines with varying sources and transformations. Data processing systems that handle different input formats, apply different transformations, and produce different outputs benefit enormously from compositional design. The ability to mix and match pipeline stages, read from files or APIs, apply filters or aggregations, output to databases or message queues without modifying core logic is powerful. The third is business rule engines, where rules combine differently for different contexts. When your domain has complex business rules that apply differently based on customer segment, market conditions, or configuration, explicit extension points are crucial. Billing systems, pricing engines, eligibility checkers, approval workflows all benefit from this approach because business rules evolve frequently and independently. Platform software that others will extend. If you're building a framework, library, or platform that other developers will build on, these principles are mandatory. You can't predict what your users will need to do. So, providing clear, well documented extension points is essential. If you have core business functions that evolve frequently, if a particular domain area changes regularly, and you have concrete evidence of this from past changes, investment in flexible architecture pays off. Look at your version history. If pricing logic has been modified monthly, that's evidence that pricing is a variation point. If customer segmentation changes quarterly, that's evidence. Don't predict based on hypotheticals, decide based on historical patterns. Now, let's also look at where you should not apply these things. Simple CRUD operations with stable requirements. If you're building straightforward create, read, update, delete operations over stable data models, the overhead of these patterns isn't justified. A user management system that creates users, lists users, updates profiles, and deletes users doesn't need compositional architecture. Keep it simple with direct database operations and simple service classes. If you're looking at performance critical inner loops, when optimizing for maximum performance, real time rendering where every microsecond matters, high frequency trading where latency is everything, low latency networking, the indirection these patterns introduce can be problematic. Virtual function calls, interface dispatches, and strategy object lookups add overhead. Profile carefully. Sometimes the right answer is a well optimized monolithic function. Now, if you're looking at throwaway prototypes where speed of implementation matters most, when validating a hypothesis or building a proof of concept that might be discarded entirely, don't invest in flexible architectures. Build the quickest thing that demonstrates the concept. Learn from it, iterate. If the concept succeeds, then invest in proper architecture for the production version. You're looking at small utilities that do one thing well, command line tools, simple script, focus utilities that don't need compositional architecture. A script that parses log files and generates summary statistics should be straightforward and direct. Don't abstract for the sake of abstraction. And systems is genuinely stable requirements. If you have a problem domain that's been solved for decades with minimal variation, for example, payroll tax calculation governed by stable regulations, scientific computations based on fixed algorithms, don't over engineer it. Sometimes the simplest approach really is the right one. Now, how do you kind of go ahead and recognize where you need to apply them? The critical skills in recognizing which category your system falls into. This requires honest assessment of your domain. You look at historical change frequency. How often have requirements in this area changed? If pricing rules have been modified 6 times in the past year, that's strong evidence pricing is a variation point worth architecting for. If they've changed once in 5 years, obviously it's not. You're looking at variation breadth. How many different variations exist across your customer base? If you have one pricing model for everyone, simple code works. If you have 15 different pricing models for different customer segments and regions, that's evidence for compositional design. You're looking at integration likelihoods. How likely are different systems integrations? If you're already on your third payment processor in 2 years, payment integration is clearly a variation point. If you use the same email service for 5 years with no plans to change, don't abstract it unnecessarily. If you're looking at orthogonal dimensions, are there multiple orthogonal dimensions for variation? If pricing varies by customer type and by region and by product category and by promotional period, these are four orthogonal axes. That's exponential complexity without proper separation. Strong evidence for applying these principles. If you have configuration needs, will this code need to support multiple contexts or configurations? If the same code logic runs differently in different environments or for different customers, explicit extension points make the configuration clear rather than buried in conditionals. Now, if you answer frequently, many, very likely, yes, and yes, invest in flexibility through these principles. If you answer rarely, few, likely, unlikely, no, and no, keep the design simple and direct. You can always refactor towards flexibility when you discover actual need. It's harder to remove unnecessary abstractions than add needed abstractions. The cost of premature abstraction is complexity without benefit. The cost of delayed abstraction is some refactoring work. Choose delayed abstractions until evidence emerges. Start simple. Add complexity only when variations actually emerge and the pain of inflexibility becomes concrete rather than theoretical.